exactly. That's the problem. Okay, so Wednesday we have the second midterm. I hadn't originally planned, but I do have, I've been working on a presentation for the two midterms that you do have, which is 2023 and 2024. And I can present them to you tomorrow or Tuesday. Tomorrow or Tuesday? Tomorrow. Okay, so when I offered it to the other section, and I didn't think about it because in their case, I'll see them on Wednesday, and then in that, I thought Tuesday and Wednesday, and then somebody came up and said, hey, how about Friday? And I said, okay. So what I'll do is, unlike my normal notes, I will give you the full notes with the solutions, not my handwriting. And then it will be, it's about 40 pages. I need to go through it to make sure I got everything as good as I can. It's a lot of pages. The midterms were not written. I didn't have a solution, so I resolved them all. Okay, so they're all solved. I think they're correct, which means that there may be errors that I missed, and if you do catch them, tell me so that next year your fellow students will benefit. Okay, so what we're going to talk about today, and I can't move around as much because the podium mic is the only mic that works, is how to use these types of non-dimensional relationships. And this will close out Chapter 5. We're done, and we will be moving on. So tomorrow, if I cover the quiz, that means on Tuesday, we will start Chapter 6 and pipe flow, and that's about 5 lectures, I think. Then the next set is the external flow, and I'll probably do something on final exams somewhere in there. So if you have a drag relationship, you can get more complex conditions when you start to look at, say, Reynolds number, roughness, length over diameter. And one of the things that you'll see in Chapter 7 is the effect of roughness on flow past a cylinder. So here, for example, is roughness that's measured as 0.02. And epsilon over d is the diameter of the cylinder. Epsilon is the height of the roughness. And you can see that it's very rough initially, and then it gets less rough, and hits smooth. Now, one of the things you should also notice is that if you ever play golf, they have dimpled balls. And the balls always have these sort of roughness elements on them. And that's why, so that they can hit somewhere, I think it's around here, so that they have a transition and lower the drag and increase the distance traveled. So what I want to do is sort of look at a couple figures and show you how you're going to use this information as you sort of go through all of these efforts. A smooth cylinder, diameter 1 centimeter, length of 20 centimeters. A cylinder is tested in wind tunnel at 45 meters per second, air at 20 and 1 atmosphere. Measured drag is 2.2 newtons. Does this agree with 5.3a, which is in the text? And I'll just make a quick note. I used an older version of the text, and so I think it's not quite the same number in the new version. All right, so I have rho 1.2 kilograms per cubic meter, mu, which is 1.8 10 to the minus 5, and Reynolds number based on diameter is 30,000. The cylinder is short, so length over diameter is a very important parameter, and that's going to be 20. And the expected C sub d for that will equal 0.91 from a table that I will show you in a minute. C sub d of the test is equal to force over 1/2 rho u squared LD, and that will equal 2.2 over 0.5 1.2 45 squared, 0.2, 0.01. And that equals 0.905. So the CD actually matches up really well. You're calculating these things for different conditions, but it's one of the advantages of using these types of already tabulated data. So for example, in my case, my students and I work in a wind tunnel. We do a lot of work looking at airfoils. There are a lot of tabulated data already out there. And those tabulated data are really helpful in sort of making sure that what we're getting actually makes sense. Another case is a chimney. So again, where we're kind of going here is we've spent the good part of this chapter sort of saying, hey, it's great, we've got the pi theorem, we can identify the important parameters, but one of the problems with those parameters is it possible to match, say, Froude number or Reynolds number simultaneously? And can I do it experimentally? So here I have a scale model, 1 to 40 reduction. Excuse me. Model is 25 millimeters, and the height is 500 millimeters. Prototype is actually 20 meters high and 1 meter in diameter. And can this prototype match up? So geometrically, this is something we're really good at. And any experiment that I ever run, geometrically, I match up very well. But my problem is matching the Reynolds numbers. So trying to match Reynolds numbers is a really hard thing to do. Experimentally, I have to run tunnels at very high speeds if I drop things by very low ratios. So if I make a chimney that is 1/20th, I need to run 20 times faster, which is not physically realistic and expensive. So if I look at that, I can say that, you know, I've got rho, velocity, diameter over mu, and I get 1.2 V1 over 1.8. So I get Reynolds number based on diameter of 66,667 times the velocity. And if I go back to this image over here, this is where I'm sort of saying, hey, I can probably get away with something in this range right here, probably in this range, because it's flat. So C sub D for my model, if it's in that range, will fit C sub D for the prototype in terms of its behaviors. But it's a very tight sort of range to go over. So if I look at that and I calculate out 10 to the 4th to 6, 6, 6, 6, 7 V, 10 to the 5th, I get a range of 0.15 V to 1.5 meters per second. So whatever I run in my wind tunnel, will not match realistic conditions, because if you go outside, you know that typically we kind of expect velocities on the range of 5, not 25 meters per second. You'd be very uncomfortable with that. But in the low range of 3 to 8 meters per second around here. But that is one of the problems with setting up these things, setting up experiments. We cannot match the physical condition. So what is the velocity range to independent as long as L over D, or L equals 20D? Geometric constraint, super. Required Reynolds number, range, okay. We do have this, so we know where we're valid and where we're not valid. And all of this is what ties in together to make and decide what exactly you're getting out. For the Reynolds number constraint, it only depends on D. And one of the things that you have to realize is you have to choose the object or the thing that's causing the disturbance or affecting your flow the most. So if I have something like this where you have L and D, the flow around that chimney is going to be most affected by the diameter. That's causing the disturbance. We kind of assume uniform flow going past it and all sorts of things associated with that. So the height doesn't play a role. We haven't, again, I'm going to sort of push back and say, hey, by the way, remember to look at that aid sheet. Just for clarification, you can bring in your own handwritten sheet. In addition, we will be providing the aid sheet that is on the announcement as part of the exam, so you can have both. That's sort of there. But if you use the aid sheet, do not print it out and run into the exam right away. Take 5 minutes to read it over and make sure you know what's on there so that you can use it. It's useless if you don't know where things are and why things are there. Okay, so I don't have figure 5.2b, I'm sorry, but I have a wire. And this is a problem, this has always been an issue. A wire 8 millimeters is singing in the wind. At what wind speed will it sing a middle C note? And that frequency is 262 hertz. And singing is associated with vortex shedding. So if you remember in the last lecture, we looked at these cases where you had this sort of regular grouping of fluid. So air would pass by a wire or a cylinder, and as it passes by, it's going to see vortices shed off of it. And vortices just mean lumps of air that are rotating together. And that happens with a regularity. So when you deal with frequencies, you always deal with Struhal number. And here I'm going to say it's Struhal number of 0.21. Typically, if I'm running an experiment and I want to look at, say, a Struhal number, I'll say 0.2. But 0.2 is usually kind of the starting point, and that's largely based on experience. Where it doesn't depend on experience, and again, in the aid sheet you'll find some of these, you'll see a whole bunch of these various dimensional groups, put them in or look at them and you can see what terms you expect. Reynolds number, always. And we're using 0.21 obviously so I can get 10 meters per second. So as you go through these problems, as you do these sorts of things, what you're trying to do is take advantage of what other people have done. People have tabulated all of these data, and what you need to be able to do is recognize what dimensional groups appear. So yeah, Buckingham Pi theorem is great, but there are other things that sort of play a role in that, and you need to know which ones to choose. So Reynolds number is UD over nu, which is 5,600, 10,008 over 1.5 times 10 to the minus 5. And at this point, again, it's on the aid sheet. I kind of made sure we put it there, but kinematic viscosity can be used for Reynolds number. So that value, and unfortunately, again, sorry, I forgot to put in the slide with the figure. The value is very close to 0.21. The assumption is good, and the wind speed is approximately that 10 meters per second, or 36 kilometers per hour. That's a very high wind speed. Generally, that's something that in Toronto, most people would find uncomfortable. So when you're doing an analysis, you have to use experience and judgment. So part of it is it's stuff that you do by doing it repeatedly. And select all the important variables that affect the process. Missing a key variable will lead to incorrect results. Adding a wrong variable will also do that. And you kind of saw that with the chimney. You could have normalized by L, but that wouldn't be the same thing, and it wouldn't give you the same sort of flexibility. Flow conditions for a model test are completely similar to the prototype if all dimensionless parameters have the same corresponding value for both the model and the prototype. And this sounds great. Pi 1 equals function of pi 2, pi 3, pi k, whatever, and pi 2 of the model equals pi 2 of the prototype, pi 3 of the model equals pi 3 of the prototype, and obviously pi 1 of the model equals pi 1 of the prototype. The reality is that you are not able to do that. And in most cases, you kind of have to fudge things a little bit. Where we have 150 plus years of experience is geometric similarity. We've been able to machine models that match up to the cases that we're interested in pretty well. A model and a prototype are geometrically similar if and only if all body dimensions in all three coordinates have the same linear scale, alpha, L of the model, L of the prototype. So for example, with airfoils, which I do a lot, we try to match the curvature here. We match any sort of point where there might be something interesting. And all angles are preserved. All features, even subtle ones, like nose radius, surface roughness, have to be scaled. So if I have a golf ball and I want to blow it up by a factor of 10, the dimples have to be increased by a factor of 10. So all of that plays a role in finally getting something that will match up here, say, for example, 40 to 4.1 meters to 1 meter, 8 meters to 0.8 meters. And the goal here is to run it in the tunnel. And the tunnel, for example, in my case, the bottom of whatchamacallit, Rosebrook, is a great place to do that, but I depend on the expertise of students and machinists to make this all work. Kinematic similarity deals with matching motion. And I'm going to try and pronounce these correctly. The motions of two systems are kinematically similar if homologous particles lie at homologous points at homologous times. Good for me. This implies model and prototype have the same length and time scale ratio. And velocity field is a scale version of the velocity field in the prototype. So for free surface flows, this is easy, right? So if you were here 20, 30 years ago, in the bottom mechanical engineering, we had a towing channel. And we had a large sort of water channel where you had a motorized scooter and you could run models down through that. And for free surface flows like that, we wanted to match it to ships or waves. And kinematic similarity is achieved if the Froude numbers are matched. No problem. Velocity squared GLM, velocity squared GLP. G in both cases are the same because we're not going to move to another planet to do this. And so velocity of the model over velocity of the prototype has to scale as the square root of the model length over the model the prototype length. And we can call that alpha. And this is a similarity of forces. And so if it's a similarity of forces, dynamic similarity exists when the model and the prototype have the same length, time, and force scale ratios. Great, great, great. All easy. And generally, you'll kind of get sort of a theme here. Incompressible flow, no free surface, match Reynolds number. Incompressible flow, free surface, match Reynolds and Froude number. Compressible flow, match Reynolds and Mach number. In all cases, we're always looking at Reynolds number. So even when you have absolutely no clue what to do, you probably are pretty safe to say, I need to get something that is related to that. And so often, I'm going to have a limit to the experiments that I can run. So 100,000 to 1 million is probably a reasonable range for what a person can, or a typical researcher can do in most wind tunnels. 10 to the 7th, 10 to the 8th are most aerodynamic flows. So I do a lot of research at low Reynolds number flows, low chord lengths, and various things like that. And when I talk about low chord lengths, I mean in this range right here. So low Reynolds number, aerodynamically low Reynolds number is anything below 1 million. And realistic, so Boeing 747, A380, all of those will be much higher, especially in operation. Which leads into the problem of complete similarity. So ideally, I would like to match everything to the prototype. So it's difficult and often impossible to do that. And it's impossible to do that because I have a lot of conflicting conditions, and I also have limits that are placed on me because my experiments are limited. So matching both Froude and Reynolds numbers means that I have to have a kinematic ratio of nu of the model, nu of the prototype, that goes as L of the model, L of the prototype, to the 3 halves, or alpha to the 3 halves. For a 1/10 scale model, we would need a model fluid with a model kinematic viscosity of 3.2% of the prototype viscosity. No practical fluid exists. There are, in the past, lots of people who did sorts of things, or lots of matching, and with very carcinogenic type fluids, and they were able to get away with it before health and safety kind of became more normal. But cigarette smoke was also really popular as tries to match it. But the idea here is that we don't have the capability to actually achieve something like this. Not in a model, or not in an experiment. So match the dominant parameter and accept that Reynolds number is mismatched. So typically what we do is we choose which one we think is the most important of the 2 parameters or 3 parameters, and we end up with different cases. Now, one of the things that MIE used to do, and I don't know if they still do, is they have tours to various facilities. And one of the better facilities to ever visit, if you get a chance, is RWDI. And RWDI is a wind engineering company that actually started out of the same lab that I run right now, but at the time was run by Jim Keffer. And the D in there is Anton Davies, who got his PhD from U of T. And they have run every large building in the world, and they've run tests on them. And they have the same problem. So even although you can see that the person there scales against the building, you know, they're probably a quarter of the size, that's minuscule to the actual building itself. So scaling to it is not going to match up. So a lot of what they do is not trying to match exactly the prototype. What they're trying to do is to identify features that are universal. And so that same thing where you have the cylinder go flat with over a wide range of Reynolds numbers, they try to do that too. So their design considerations: wind force on the structure, flow-induced vibrations, and building motion tolerance for occupant comfort. And so they've done all of these. So it's actually quite impressive. And what's scary is that on each of these, they tend to put in very small pressure taps and thousands of them. The people who do this, the technical work that's involved with that is actually quite astounding, and the modeling is really impressive. So they are doing more CFD than they did in the past, but they also remain sort of preeminent in that area. So in hydraulic modeling, Froude number is matched, and the Reynolds number is often too low. We can't match it for ships, we can't match it for flows, and model data has to be extrapolated to predict prototype performance. And it introduces some uncertainty. So the way you get around it often is to say, hey, I have a bit of experience in this area, and this is how I'm going to translate that up. I have a prototype airplane, and it has a chord length. Chord length is associated with the wing. So if you have a wing, and I can sort of tap, tap, tap through there, that is the chord length. So just the length of it is 1.6 meters, flies at Mach 2 at 10 kilometers altitude, and I want to use a 1/8 scale model in a helium wind tunnel. And using helium is a way to get around the Reynolds numbers issues. And if you're interested in work like that, there's a group, Marcus Hultmark, but Lex Smits at Princeton, who did that years ago and set up a really impressive facility that requires unbelievable amounts of precautions in order to run it. So the typical student is going to unlock the door to a pipe, put the model in, shut the thing down. You've got to be really careful with that, and then run the tunnel and then hope everything works out. And helium is a very expensive thing to have run. I'm going to use A, that's not acceleration, that's just velocity. So I have velocity of the prototype, 600 meters per second. Velocity of the model is 1134 meters per second. Model and prototype densities differ by a factor of 4, and model prototype, model to prototype viscosity is about 50% difference. Specific heat ratios between the two are 1.4, 1.6. They're close, but they're not going to match really well. So matching the Mach number, I have velocity of the model equals Mach of the model times acceleration of the model, and I need to get 2268 meters per second. And for the Reynolds number, rho of the prototype, velocity of the prototype, length of the prototype over mu of the prototype is 26.6 times 10 to the 6th prototype. Reynolds of the model is going to be rho of the model velocity of the model, length of the model, mu of the model, which is equal to 2.56 times 10 to the 6th. So already I can see that I'm not going to match Reynolds numbers. I have a ridiculously high Reynolds number already, but I'm off by a factor of 10. If I try and match things up, I can put in all of those same values, match the Reynolds number, and my velocity of the model would have to be 23,600 meters per second, and my Mach number of the model, velocity of the model, over A of the model is equal to 21 Mach number. This is hypersonic, which chemically becomes more complex and is absolutely ridiculous. And so I am not able to match conditions. So again, as much as I can, when I'm running these cases, I'm trying to keep things as close as possible and that I can extrapolate out to. And then I have the specific heat ratio, and that's still different, and there's different thermodynamic behavior. Any questions on this one? So the U.S. Army Corps of Engineers has built a scale model of the entire Mississippi. And again, geometrically, it's probably kind of compressed. I don't know what the ratios are. But Froude number can be scaled, so they can do that pretty well. But the Reynolds number cannot. Because you've got something that is a couple kilometers wide. No matter how much scaling you do, you're not going to match up Reynolds numbers. But it's kept high enough to ensure the model is fully turbulent, which we can do. You pump, you pay a lot for pumping, which is a reasonable approximation of the prototype's viscous effects. So as you're looking at these different types of facilities, they were sort of the benchmark, and they still are, in terms of what you look at for data. So I can also look at pressure drop as in a pipe as a function of velocity, density, mu, L, and D, do all the pi groups, and I'll get that the pi groups should be a function of length over diameter and Reynolds number. And you can see that all of these correlations sort of go all over the place. So you have 200 down here, you have 100 down here, you have 700, you got 900 for different L over D ratios. So the L over D is not very helpful. I'll talk more about the other one in a second. However, for long pipes, it's known that delta P is proportional to L, and we can rewrite these and combine them. And so instead of having 3 pi groups, we kind of combine them and make 2 pi groups, and we end up with pi 1 over L over D, and we end up with this relationship right here, which is a linear relationship that goes as Reynolds number and pi 1 over pi 3. And again, you're going to see a lot of data out there where we've taken some form of the data that we had that kind of scatters all over the place, replotted it in a new form, and those 9 data points collapse into a single power law curve, because you kind of expect Reynolds number and length to sort of be correlated. You're not expected to figure that out on your own. You are expected to know when to look at tables. So looking at tables, looking at charts, this is where you spend a lot of time as engineers. You can do the same thing. So if you remember way at the beginning, I did that plot, or I showed you that plot that looked at the standard drag chart, CD versus Reynolds number, and you could see, for example, there was a lot. CD versus Reynolds number, right here. So you can see what that looks like for a cylinder and for a sphere. So the standard drag chart is difficult to use if you know the drag force. So if I know the drag force, I want things in a way that kind of makes sense. So I can use C sub D, but C sub D is not super. And you need to find velocity. Say you have the drag force, you need to find velocity. So you rerun the dimensional analysis and you create a pi group where F and V are separate. So you use rho, mu, and d. You get pi groups that are pi 1 rho F drag over mu squared, dimensionless force, and Reynolds number. And again, largely when you look at these problems, you're going to see Reynolds number of over and over. So drag force. Okay. Drag force. Force of drag equals weight net. Oh, sorry. Find the terminal velocity of a 1 centimeter ball, specific gravity 7.86, falling in water. In which case you have net weight, rho s minus rho w, g pi over 6, d cubed. So all you're doing is you're taking kilograms per cubic meter, multiplying it by gravity, and when you do that, you're also multiplying by the volume of the sphere. And that will equal 7844 minus 998, 9.81 pi over 6, 0, 1 cubed. And force of drag equals 0.031 or 51. And so your rho F over mu squared is 998 351 001 squared 3.5 times 10 to the 7th. So I have a number that I can use right away. And what I'll do is I'll read that off of my chart over here. So if I have 3.5 times 10 to the 7th, it's somewhere here. And it is 3.5 times 10 to the 7th. About 2 times 10 to the 4th. So that's an easy chart to read from as compared to the other one. So if I do that, I get a corresponding value of 2 times 10 to the 4th, solve for the velocity. So Reynolds number equals rho velocity diameter over mu, which equals 20,000. Which equals 998 V 001 over 001, and a velocity of 2 meters per second. If you were to do it with the other chart, you'd need to do iteration. You have to go back, check your result, see if it makes sense, go back, check your result again. And we're going to do iterative types approaches in the next chapter when we start to look at the Moody diagram and also an alternative, which is the Howland equation for that. I'm going to do one final example. I'm going to go back, but here's sort of the conclusion of this chapter. This is probably the best chapter in terms of understanding what physically is going to happen in the next two chapters. We're going to use a whole bunch of these dimensional parameters, slap them into various tables, into charts, and use that as a way to extract out things. But ultimately, the goal here in this chapter has been model testing to achieve similarity between a model and a prototype. And we try to do geometric similarity. That's easy. We have very, very highly talented machinists in this department and around the world who can do it with their eyes closed. Well, not quite, but okay. Kinematic similarity and dynamic similarity, which depends on money to a certain extent. If I had a lot of money and I could sort of rip the center of King's College Circle and make the wind tunnel of my dreams, I still would not be able to get anywhere close to the numbers that I need to achieve. So you always make choices, you always make different types of decisions. Complete similarity is often impossible. You can't match all relevant dimensionless numbers. Say, for example, Reynolds versus Froude number, Reynolds versus Mach number with common fluids. And we work with common fluids, one, because it's a lot easier. If I have a tunnel, I'd rather work with air than try to put together a helium tunnel. Judgment is important. You have to identify dominant physics, and that's part of the experience, but it's also part of just looking at what other people have done. That table of dimensional groups should be something that you depend on to sort of guide your pi theorem sort of approaches. Understand the limitations and techniques like extrapolation, where I said, hey, I've got Reynolds number 10 to the 4th. I'm going to extrapolate this feature to 10 to the 5th. Well, maybe that's okay. I certainly can't do it to 10 to the 6th. Dimensionless charts can be replotted and manipulated to solve problems directly and reveal deeper physical insights as seen in the pipe flow and falling sphere examples. The other thing, too, is honestly, nowadays you don't use a lot of that. You have a lot of tools in terms of computational databases to help with that. Okay, any questions on this one? Okay, I got a question about this, and I kind of sort of skipped it in lecture 24, and I thought it was kind of a neat problem. Express the tip deflection delta of a prismatic cantilever with end load P, so it's just something like this, where we put a P on there. And dimensionless form using length L, area moment of inertia I, and Young's modulus, so F, P, L, I, and E. Assumptions, small deflections, the end load is static, and we have a variable count. That's easy. Every time you do this, you can have delta, P, L, I, and E. And really what the important point here is that the dimensions M, L, and T you'll find the original example there. I also gave you the answer, but I want to give you a bit more information. So 0, 1, 0. Delta is a length parameter. Okay. Force is 1, 1, minus 2. Length 0, 1, 0. I is 0, 4, 0. And 1, 1, minus 2. So what should stick out to you right away is that P and E have both the same order for M and T. So if you started to do any type of analysis on that, you'd get rid of it. So effectively, It's two-dimensional. So here, j is equal to 2, even though you have MLT terms. And so when you do that, your k is equal to n minus j, which is 5 minus 2, which equals 3. So you've kind of lost some of this that you had before. And I only have 2 base parameters, so I'm going to try P, L, and E, and that's probably the most sensible ones. So for pi 1, I'm going to use delta, L to the A, E to the B, and it will end up, I just want to see how much time I have, MB T minus 2B, or, yeah, L1 plus A minus B. And I end up with B equals 0, that's the only sensible result, and A equals minus 1. So pi 1 is delta over L. Pi 1, pi 2, PLA, EB. And I'm just going to jump ahead a little bit, and you are free to do these on your own. I'd recommend you try this. The hard step was the initial step. The hard step was trying to figure out that you have 2 dimensions that you got to work with. After this, it's just choosing the terms that you look at. So it's the load group. And from then finally, pi 3, which equals I, L, A, E, B, and pi equals I over L to the 4th. So delta over L is a function of P E L squared I L to the 4th. I'm not a structural engineer. I don't pretend to be. This is actually kind of useful, though, because even with that sort of limited knowledge, I can say, hey, delta over L, or sorry, beam theory, delta is equal to P L cubed over 3EI, and that equals 1/3 of pi 2 over pi 3. So what's really impressive here is that without really knowing very much about the problem, other than the step where I said, hey, look, M and T sort of are not useful variables really, I'm able to get something that matches pretty well, and the pi groups actually match up with what's expected. Any questions on this one? Go ahead.
Could you go over again, when we're looking at P and E, the reason why you say that they're going to cancel, it's just like the intuition of
This is a hard problem.
and how they cancel each other out, like how like you can look at that before analyzing it to determine something.
So any combination of P and E is going to cancel out the M and T. And they're the only ones here that have those. So I have to decide which one's the more important out of the whole set. And so this is that step, and you're right, this is the intuition step. Once you see all of that on a table, you say, hey, those 2 terms are repeated. I don't want to use that. And physically, the load is the more important term that I'm going to look at. But making that decision and going through all of this is easy on paper and lecture. It's hard to do it on your own. So you need to sort of wrestle with that a little bit. And this is where we start.